Promax Combustion. Fire done safely.
Hello everyone, and welcome to Promax University. This is the first module in our Combustion 101 series discussing the basic chemistry of hydrocarbon combustion. Before we dive into too much detail, it's important to point out that all of our presentations are geared towards industrial combustion applications. Combustion is a very broad topic. Cavemen discovered millions of years ago just how powerful the exothermic reactions of combustion could be. However, the purpose of our Combustion 101 series is to help gas technicians, combustion system designers, and machine operators develop a better understanding of how and why flames behave like they do. This particular module will discuss the required elements for combustion, what are hydrocarbons, enthalpy of formation, and the heat of reaction. Three basic elements are required for any combustion reaction to take place. The most important ingredient is fuel. For most industrial combustion processes, this could be natural gas, propane, oil, or even coal. Although the mechanisms for burning gases, liquids, and solids are completely different, the underlying chemical reactions are essentially the same. The second ingredient is an oxidizer. The large majority of industrial applications use air as the main oxidizer, but there are instances where pure oxygen or even fuel-bound oxygen is used. The last ingredient to get combustion started is an ignition source. It takes a flame to make a flame. Think of using a match to light a candle. But on the industrial scale, to heat things up, we normally use a high voltage spark. So what is combustion? It's using fuel, mixing in a specific amount of air, adding an ignition source, and presto, we have combustion. This yields combustion products, light, and most importantly, heat. To simplify our discussion about combustion, we're going to limit our examples to gaseous hydrocarbons. Now, what exactly are hydrocarbons? In English, this means fuels that are comprised of mostly hydrogen and carbon atoms and are readily available as a gas. The two most common hydrocarbons used in industrial applications are natural gas, also known as methane, and propane. Methane is a single carbon atom surrounded by 4 hydrogen atoms. Ethane is 2 carbon atoms surrounded by 6 hydrogen atoms. Propane is 3 carbon atoms surrounded by 8 hydrogen atoms. Butane is 4 carbon atoms surrounded by 10 hydrogen atoms, and so on and so on. For the purposes of this discussion, we're going to look at the chemistry behind methane combustion. For every methane molecule, the process requires 2 molecules of oxygen. This will yield a carbon dioxide molecule, 2 water molecules, light, and heat. The important lesson to learn here is that because the amount of carbon and hydrogen differ from fuel to fuel, so does the amount of oxygen required to complete the process. 1 molecule of propane requires 5 molecules of air and generates 3 molecules of carbon dioxide and 4 molecules of water vapor. Now, regardless of the chemical composition, what we really need to emphasize here is that the generation of heat is the driving force behind most industrial combustion applications. Although the chemical reaction may have desirable benefits, the main reason we burn fuel is to obtain heat. So where does the heat come from when looking at the combustion of methane? Although this is an incredibly complex question, one can visualize the answer in a relatively simple way. Every compound in the universe stores a given amount of energy within its molecular bonds. The energy within these bonds is known as the enthalpy of formation. In other words, a molecule of methane stores energy in the 4 carbon-hydrogen bonds of the fuel's structure. The same is true for the double oxygen bonds within each oxygen molecule. When the methane and oxygen molecules are dissociated by the combustion process, energy is released. Because of the now readily available energy, the combustion products form into a new set of molecules. Carbon dioxide forms new carbon-oxygen bonds, and water vapor forms new hydrogen-oxygen bonds. These new combustion product molecules absorb some of the available energy. When the energy released is greater than the energy absorbed, this is called an exothermic reaction. The leftover energy from the methane combustion process is converted to the heat that we use in our furnaces boilers, and other combustion processes. The net difference in the heat released and the heat absorbed by the combustion process is called the heat of reaction for a given fuel. Interestingly, most hydrocarbons have very similar heat of reaction values. As you can see from the slide below, the hydrocarbons most used in industrial applications all yield about 20,000 BTUs per pound of fuel. Methane ranges from 21,495 to 23,875 BTUs per pound. Ethane ranges from 20,418 to 22,323 BTUs per pound. Propane ranges from 19,937 to 21,669 BTUs per pound. And butane ranges from 19,678 BTUs to 21,321 BTUs per pound. So, what have we learned? Well, we've learned that all combustion processes require three things: fuel, oxygen, and an ignition source. Hydrocarbons are comprised mainly of hydrogen and carbon molecules. When we break up hydrocarbon molecules, energy is released in what is known as an exothermic reaction. The purpose of combustion on an industrial scale is to generate heat. The energy from combustion molecules is stored in the molecular bonds of those molecules, and most hydrocarbons yield the same amount of heat per pound.